Select the major product of the following reaction. So if we look at what we are given here, we can see that we have a Grignard reagent. So hopefully you can recognize that by that carbon-magnesium bond. So we have a Grignard reagent. And what we want to recognize here is that when you have a carbon-metal bond, then you have something that's actually going to act as an anionic carbon. So we can look at this Grignard reagent almost as though we have a carbanion, because we have an extremely polar covalent bond here. And the magnesium is more electropositive than the carbon. So we pretty much have something that can act like this. And then we have the magnesium bromide we can think of as the counter ion. And you could also draw that as a covalent bond, but it might be a little bit easier for you to see the nucleophilic carbon if you represent this as ionic. And so this is a really, really strong nucleophile and a strong base. So it is a strong nucleophile and a strong base. So then we want to see what we're reacting it with to see if we have any acidic hydrogens or any electrophilic atoms. And so we are adding an acetone to this. So we are adding in this first step, we can redraw this acetone as CH3C, our double bond O, and the other CH3 group. So this is a ketone. And so the carbonyl here is electrophilic because we got that double bond to oxygen. So we can then assume, okay, we've got a nucleophile, we've got an electrophilic carbon, those are going to react with each other. So this CH2 group is going to form a bond to that carbonyl carbon. And we've seen this pattern quite a few times. When you have a nucleophile attack a carbonyl, then you break that pi bond and push those electrons up onto the carbonyl oxygen. So let's take a look at what this is going to form. So we have the benzene ring with that CH2 group, and the new bond formed between this CH2 and that carbonyl carbon. So I'm going to represent here is our new bond, and then we're going to put this, I'm going to keep the color coding so we can keep track of our carbons here. So this was the carbonyl carbon, and so it now has a single bond to oxygen and a negative charge because we put an extra lone pair of electrons in the oxygen, and it also still has those two bonds to the methyl groups. And so this is your tetrahedral intermediate. And so whenever we see a tetrahedral intermediate, we want to take a look at it and see, is there a good leaving group? Because if there is, we know that these electrons might come down to reform the double bond and push off the leaving group. But if we take a look, all of our bonds are to carbon. And so a carbanion is a really, really strong base and a terrible leaving group. So we are not going to have anything leave. So this molecule is just basically going to sit just like this as the anion until we do a workup step when we can add a proton. And what we're adding, actually, in this case, instead of a proton, we're adding a deuterium. So deuterium is just an isotope of hydrogen. So this is a heavy hydrogen. So in this last step, we can draw this in. It's going to look exactly the same. So we have deuterium, OD2+. So this is just, it's going to function the same as H3O+. Okay, so we can say then that this lone pair of electrons will react with the deuterium and break that oxygen deuterium bond so that overall we will have formed this molecule. So we're going to have an O with the deuterium and the two CH3 groups. So you can see that that is the same as option D.